Hello, once again, this is Numerical Methods. Our topic for today is all about numerical differentiation. Yours truly, Engineer Paulina A. Marzan. In numerical differentiation, let us say given a function f of xi and a step size or interval of h, to find for the first derivative of f of xi and or the second derivative of f of xi, the following numerical methods and formulas may apply. We have the simple accuracy formulas, particularly the forward difference formula, backward difference formula, and the central difference formula. We also have another that's for the high accuracy formulas, specifically the forward difference formula, backward difference formula, and the central difference formula. So for the forward difference formula of simple accuracy, this is the formula for the first derivative of f of xi, and this is the formula for the second derivative of f of xi. For the forward difference formula of high accuracy, this is for the first derivative, and the formula for the second derivative. For the backward difference formula of accuracy OH, or the simple accuracy, this is for the first derivative, this is for the second derivative. For the backward difference formula of high accuracy, this is for the first derivatives of f of xi, and this is for the second derivative of f of xi. For the central difference formula of simple accuracy, this is used in getting the first derivative of f of xi, and this is for the second derivative of f of xi. And we also have the central difference formula of high accuracy for the first derivative of f of xi and for the second derivative of f of xi. Okay. So example, let's say we are going to estimate the first and second derivatives of the function below, okay, f of x at x is 2.5 using the simple and high accuracy formulas and a step size of h, which is equal to 0.2. Okay, so below is the function and we are going to differentiate it. Okay, so that's the given f of x. If we are going to find the first derivative of it and the second derivative of it at x is equal to 2.5, we need the following data. So from the given, h is equal to 0.2, that's the interval of points. So the given xi is 2.5. So if we are going to substitute xi to the given f of x, we will get this f of xi, which is equal to 81.9375. And if we are going to take the next higher step value of xi, that will be 2.5 plus 0.2, we will get xi plus 1, that's 2.75. And if we will substitute 2.7, I should say, if we will substitute 2.7 to the given f of x, we will get this result, that's 108.4137. Okay, so we also need the next higher step value of x, that's the 2.7 plus 0.2, we will get xi plus 2, which is equal to 2.9. And if we will substitute or use 2.9 to evaluate f of x, that's the given, we will get f of xi plus 2, which is equal to 141.3227. Okay, so in addition to use the other formulas, we also need this value. Okay, this is the xi minus 1. Xi minus 1 is the step down value of 2.5. Okay, that's 2.5 minus 0.2, we have 2.3, and substituting this to the given function, we have 60.9677. And also, to get the next lower step of our x, we have 2.1. That's 2.3 minus 0.2. We were able to get 2.1. And substituting this to the given f of x, we have the f of xi minus 2, which is equal to 44.6547. Okay, so using the forward difference formula of simple accuracy to get the first derivative of f of x and also the second derivative of f of x, just substitute those values or those data to the formulas and you will get the results. Okay, so we will get, for the first derivative of f of x using this formula, by substituting 2.5 to the formula okay, the first derivative of f of x at 2.5 is approximately 108.4137 minus 81.9375 all over 0.2. Okay, and that is approximately equal to 132.381. So that's the first derivative of our f of x at x is equal to 2.5 using the forward difference formula of simple accuracy. And now for the second derivative of the f of x, it is approximately equal to the f of xi plus 2 minus 2 times f of xi plus 1 plus f of xi all over h squared. And substituting 2.5 to that formula, we will get this. Okay, 141.3227 minus 2 times 108.4137, that's the value of xi plus 1, plus 81.9375, that's the value of f of xi, all over the value of h squared, that's 0.2 squared. So by computing, we will get the value of 160.82 for the second derivative of f of x at 2.5. Okay, so therefore, given the function f of x, which is equal to 2x raised to 4 minus 1.5x raised to 3 plus 5x squared minus 4x plus 6, through the use of the simple accuracy forward difference formula, when x is equal to 2.5, the first derivative of x is equal to 132.381 and the second derivative of f of x is equal to 160.82. 0.82. For the other formulas, same manner will follow. Just substitute the corresponding values into the formulas, then you will get the results. If you will notice later on, you will find that the result in, let's say, deriving the first derivative of the function in the forward difference formula and the backward difference formula and the central difference formula might be different. Okay, so there's a difference in terms of the result. Okay, so that is because the results may vary from one formula to the other. So which is the most accurate? I can say that's the central difference formula. You can check it by first you apply a differential calculus to differentiate the given f of x and substitute 2.5 to the first derivative of f of x by differential calculus. That's the real answer. So if you are going to compare that to the results in the numerical solutions by numerical methods, okay, you will get the variations and you will come to know which one is the most accurate. And I can say that's the central difference formula of high accuracy. The formula is quite long, but the result is very close or as close as the real result. That's all for this topic. Thank you for watching.